be talking about today is the work that we did at JPMorgan Chase in collaboration with IBM on the problem of option pricing using quantum computers. Right? You might have seen some stories in the media about that make some catchy titles, and what I'm here to show is precisely what we're doing, and kind of take away any doubts and of what the media might give to you to believe, let's say. So let's see. So just a little bit of background, right? Of what are we doing? What's the group in the firm that looks at that problem? So one thing to keep in mind is that as a firm, we spend more than $11 billion a year to be at the forefront of technological innovation, and that includes resources for computing power, research into algorithms, and all the various processes that need to be done to guarantee the best products for our clients. And we have been a member of the IBM Q network since late 2017. And a lot of us at the bank, we have physics background, and when the opportunity to work in quantum computing came up, we were all very happy, and we jumped at the proposition to help in that field. So what we've done is that we've established the quantum working group in the firm, which includes full-time researchers, which try to provide an expertise in the domain of the problems we're interested in, and live in that boundary of where that expertise starts to overlap with quantum computing. And our goal is to, in general terms, is to identify the promising use cases for our business, develop, if possible, prototypes for these promising use cases, and probably most importantly, understand the potential impact of the field in our business. And I guess you could say there's two reasons for that. Well, if there's a significant impact of quantum computing in our business, then we want to be there to take advantage of that. And on the other side, if somebody comes to us and says, hey, I can use quantum computers to do this problem really fast, then we can tell them, great, well, show us how. And then we'll be able to understand and verify or see if these claims are true. Right? So why are we focused on option pricing? Why is this one of the projects that we're interested in? So option pricing is a huge part of our business, and the ability to price these option contracts, which I'll go into a little bit more detail in a little bit, is very imperative for effectively managing risk across other purposes. And most of the practically relevant options, they're too complex to price analytically. So more often than not, we have to rely to numerical methods for pricing these contracts. And Monte Carlo is one of the most popular approaches because of a variety of features that are desirable. It's very flexible, so it can handle with a generic approach pricing across different types of contracts. So the overlap with quantum computing there is that amplitude estimation is one of these fundamental quantum computing algorithms which can provide a quadratic speed up in problems that employ Monte Carlo methods. So there's an equivalence that we wanted to explore in that space. And there's existing research on these approaches that are doing an equivalent thing to Monte Carlo, which has yielded promising results. One of the main approaches is from Ashley, who you just heard his talk. Our colleagues from IBM have done some work on that already, and our colleagues at Xanadu as well have done some work on this problem. Okay, so we are Q2B, and the title of the conference is Practical Quantum Computing, and that's where we want to be. We want to be in the practical side of things. So our goal of this project is to sit down and implement the quantum circuits required to implement these amplitude estimation methods on a quantum computer, and then examine how the resources scale when you start adding complexity to the models. So our approach is, let's start with something simple. Let's see if we can create the circuits and see what is needed for this approach to work. And then once we start adding complexity to option types that are where the interest lies in our business, which are hard to price, then let's see if that scales, right? Let's see if that is an avenue for the future or not. And the last thing, which is mostly for understanding how far away we are today from a time point that this quantum computing effort will have an impact on our business, let's try and see if we can run anything on today's quantum devices. And so everything that I'll talk today is included in a paper that's available on arXiv. I'll try to go over the main ideas, and I will refer to the paper for the details about various components. Okay, so I'll quickly go through the basic idea of an option, right? Fundamentally, it's a simple concept, so I don't think we'll have too much trouble in this talk. An option is a contract between two parties with an agreement of a possible future transaction with parameters, some parameters decided upon today, right? So the one simple use case is that in 6 months from now, you have the option to buy an asset X from me at price Y, right? So in 6 months, let's say you have the option to buy JPMorgan stock at $100, right? So this is the contract that we enter in. So why would you want to do that? Why are these useful? Well, one of the simplest things you can imagine is that if you think that the price of asset X in 6 months will be higher than Y, right? Then you can buy that asset from me at Y and sell it at the market and make a profit. Right? That's the simplest way to think about it, but there's other features of this contract which are used for hedging risk. Right? And the question we're trying to answer, so what is that contract worth today? Right? So if I sell you that contract, if I give you that option, I should charge you something, right? So that, or how much should I charge you so that it makes financial sense for me to enter this contract, and vice versa, right? You want to do the same thing. And this is a very simple use case, which is easy to understand, but these are complicated contracts. Options are complicated contracts whose value derives from one or more sources of uncertainty implied in the future direction of the market. And options are a type of derivative, and derivatives are called derivatives because they derive the value from some other quantity. Right. Okay, so what do we do now for pricing these contracts, right? So as I mentioned, there's a few ways that you can price these contracts depending on their dynamics and the qualities. But you can think of these contracts as having an associated payoff, right? Defined on some domain of underlines with uncertainty, right? And this payoff can be something very simple, like what I discussed so far, but it could be something much more complicated, where it depends on a number of underlying assets, and it can depend on their value in multiple times in the future. And so we need something that's flexible and able to price all of these contracts. And Monte Carlo is a very straightforward approach, where assuming a particular model for how we think asset prices evolve in the future. So simple case, you can say, okay, well, I assume that these assets follow geometric Brownian motion, and then I can simulate some of these possible paths in the future. So assuming some of these, some underlying dynamic, then we can simulate these underlying assets until the time that our agreement specifies, and then calculate the expectation value of that payoff as an average over those simulated paths, right? And so you can see an expression I have for the expectation value. There's a little bit more into it, but just for the sake of this argument, you can think of it as an average, right? We want to compute an average over some quantity over these different paths. So for the European call option, which is what I described, the brief use case, then the payoff of the option which is I denote as F. So at time t, capital T, which is the point that our contract specifies, then it will depend on the value of that asset at that particular point in time, and it will be the maximum of 0, or the difference between the value at the exercise date, let's say, and a strike price that we agreed upon today, right? So in the lower graph, you can see how the payoff essentially behaves as a function of that value of the asset at maturity. So if in this particular case, this is an asset where the strike price K is at 1.9. So if at maturity or at the exercise date, if the value of that asset is below 1.9, it doesn't make sense to exercise your option to buy that asset. But after that, it becomes valuable. Now, when we use Monte Carlo approach to price these options, the error of the approximation, which we do, scales as 1 over square root of m, right? So m is the number of paths that we decide to simulate and take the average over. And obviously, the more of these simulations we do, the more accurate our price estimate will be. But this square root convergence means that if we want to halve the error in our estimation, we need to quadruple the number of paths that we take, right? And so even though Monte Carlo is flexible and it's a decent approach and easy to code up and extend to different option types, the convergence is quite slow. Right? Okay, so what are we going to do in our quantum approach? So there's 3 basic steps that I will briefly go over, and then I'll go into more detail in the later slides. So the first idea is, given that we have, we make an assumption about the underlying dynamics of the assets, right? There is an implicit probability distribution for assets for the asset price in the future. And so we can say, okay, at my maturity date, I have a formula of probability distribution of the asset prices, and then I'll use n qubits, little n qubits, so I can represent 2 to the n possible asset prices at that point in the future, right? And so each basis state will correspond to one of these possible asset prices, and the amplitude of this of each basis state will correspond to the probability that my model implies about that being true at that particular moment in time. And we can think of a situation where we say, okay, I'm interested in a particular range of asset prices at maturity, and I will discretize this range using 2 to the n states, where little n is the number of qubits I choose, and then I can construct my state to look like something in the top graph. Okay, so let's say I'm able to do that. Then what? Then the second step is that I need to construct a circuit that can compare the asset price, which is represented by each one of these basis states, to the strike price of the option that we've agreed upon before we enter the contract. Okay, let's say I can do that. Then what? Okay, then the last step is we need to, in the construction of these circuits, is I need to come up with an operator that we'll call A, which will operate at an initial state. It will load this distribution and then perform a rotation into an ancilla qubit, where the amplitude of the 0 and the 1 state will tell us something about the value of the option. Right? So in the right-hand side of what you see here under item 3, the amplitude of the 1 state in the ancilla holds information about the price of our contract. Right? Now, if we're able to do these 3 steps, then we can use amplitude estimation with m qubits to estimate that amplitude with the error that scales as 1 over m, and this m is the number of times that we call this A operator that we need to construct, right? And what that means is that if you can compare that to the number of times we need to compute the payoff function over these Monte Carlo paths, then you can say that you can have a quadratic speedup compared to Monte Carlo, right? So 1 over square root of m becomes 1 over m. So theoretically, if you wanted to halve the error in this approach, you would just need to double the number of samples that you take the quantum samples, let's say. What we get out of this amplitude estimation is something that is proportional to the value of the option as we defined it. So I can go ahead and do this approach and then do a simple transformation to get back the value of the option. So this is the general approach, right? I haven't gone into details, but hopefully that makes sense. And our focus in this work was to see what it takes to construct these A operators and the operators that depend on A to carry out amplitude estimation. Okay, so for the first part, right? So how do we load the uncertainty into our basis states the way I described, which is the first step that we need to do? Well, it turns out that there's the most interesting approaches that we found. There's three of them. One of them is using multiplexers for preparations of quantum states. So the idea there is that given a random state that you want to construct, there is a recipe that you can deconstruct that down. Assuming you've started with that, you can deconstruct it down to the 0 state. So then you can reverse it and generate a random quantum state. Another approach is one that was described in a paper by Grover and Rudolph, which claims that you can represent efficiently integrable probability distributions on your basis states. And the third approach, which was developed by or studied by our colleagues at IBM, you can use quantum generative adversarial networks for learning and loading random distributions, right? So, okay, so the first one is kind of simple conceptually to understand, but it scales as exponentially with the number of qubits that we use. Okay, the second one scales linearly, but it's practically hard to do. There's a lot of unknowns about how to do these rotations, and it implies that you're able to do efficient integration probably on the circuit, which is not very clear. And the last method is that you have a choice of the variational ansatz you can use, but there's training required. And once you have that, it's harder to estimate how much, what speed up you get, if you get any speed up, how that fits in that whole overlook of whether this is useful or not. So we're hoping that perhaps we'll be able to use the second approach at some point, but in our work we've used mostly the third approach because it allows us to create some circuits that we can analyze and see how to proceed with the problem without getting stuck in this. But we should make it very clear that this is a tough problem, and we need a good solution to this problem to be able to make progress in this area. Okay, so the next thing that we need is a strike price comparator, right? That was a number 2 in the steps that I outlined. So in this plot here, you can see that distribution of states that I mentioned before, and there is a red dashed line representing the strike price, which is 1.9, I believe, for this particular circuit. So what we need to do, or our approach, is to take an ancilla qubit and then create a circuit that sets that ancilla qubit to 1 if the basis state is larger than the strike price, and 0 if not, right? And then what we can do is that we can use that ancilla qubit to decide which of the basis states will contribute to the value of the option, right? So one particular example for this representation, you can see in the circuit below. So P of X, I leave it opaque for now, so that this loads the probability distribution. It can be one of the 3 approaches that I outlined before, and then we came up with a circuit that is quite efficient to do this comparison. And one of the key ideas, one of the key concepts here is that in constructing all these circuits that play into this option pricing, we need to make sure that they are efficient, and we can construct them efficiently. Otherwise, we risk losing any advantage that will come from that. And we have we have come up with a way to do this efficiently, and the details are explained in the paper. Here you can see actually this is a simple logic circuit that checks if either the last 2 qubits are both set or the first qubit is set. Well, depending on how you see the order. But it's we want to be able to represent all sorts of quantities as the asset price, so we're not limited by integers. We can represent real numbers, and we're able to create the circuits as a black box, essentially, just by knowing the distribution and the strike price. So that's one thing that we've achieved. Then to encode the option payoff into the amplitude of the ancilla qubit on which we will do amplitude estimation, we have a linear payoff in our case. So thinking about this European option in the simplest terms, and the idea there is that we can use controlled Y rotations. Which are the control qubits are the qubits representing the state of our asset, and then we can create this rotation as a sign of a function into the ancilla qubit. Now, in order to represent this exactly, we need to create a circuit that computes the arc sign of a function. But there's a trick that we can do where we can take advantage of some Taylor expansions and represent this approximately, but in a way that still maintains speed up compared to classical method. And this method was described in a quantum risk analysis paper by your IBM colleagues, so I refer you to that for more details if you're interested. And then with that, we have all the components that we need to price these options. So we can set up the simulator and try to see how this approach works in practice. So in the graph here, you can see this red dashed line corresponding to the analytical value of an option that we picked to simulate, and then the convergence that you get once you increase the number of amplitude estimation samples, let's say, right? The quantum samples that are represented as amplitude estimation. And the idea is that with amplitude estimation, we can get this 1/m convergence to the price with a high probability, which is 8/pi squared, which is a little bit than 80%. This is one of the things we wanted to come up with to make sure that we can create the circuits to do this approach to price an option. And at this point, it's a simulated version. And another thing we wanted to verify was, okay, so we have this expected speed up. How does it compare practically, right? So we took an example option, we priced it using Monte Carlo, increasing the number of samples. So here you can see the green X's correspond to the estimation error from a Monte Carlo approach. And this is the dashed line is a fit. This is a log-log scale. And we can do the same thing with the amplitude estimation approach and simulate it and see how it scales correspondingly, right? So you can see the predicted or the expected difference between the convergence of the two methods. And this was something that we were happy to be able to construct and see as a verification, right? Okay, so far I've talked about how the components that are needed to create a circuit that will be able to encode the price of a European option to use amplitude estimation. But this is a very simple use case that we actually don't even need to simulate. We can solve it in most cases, in a lot of cases analytically, depending on the model. So let's start to add some complexity, right? And so what are we doing there? And the simplest complexity we can add, the simple level of complexity, is to, instead of focusing on one underlying asset, we can look at a basket of assets, each one that comes with a corresponding weight, and then the equivalent of the asset price in the previous case is now a linear. It's a weighted sum of the asset prices of the basket, right? And then our payoff is a little bit more complicated. Instead of having a single asset, we have a weighted sum over there, right? So our approach there is that we can use D registers if D is the number of assets that we have. We take the same approach as the European option use case, pick a range that we're interested in for asset prices for each one of these assets, and then load the distribution into the collection of these registers for each of these random variables that we're interested in, which are the underlying assets. And then we, in order to be able to do the amplitude estimation approach to this, we need to create a circuit that computes this weighted sum that takes the inputs, the qubit registers for each one of the assets, and computes a weighted sum into another register, which will hold essentially the value. We will treat this process as if it was a separate asset with a distribution of possible prices. So we came up with an efficient way to do this, to implement this component as well. And which scales satisfactorily for these problems. And then once we have this weighted sum operator that we can compute the sum on the circuit, we can then continue with the strike price comparator and the encoding the payoff into the ancilla qubit. So this is a simple generalization. What we take out of this is that we don't come across some problems that introduce some exponential dependency on some parameter that we have, right? Which is what we wanted to check and verify or not, right? Okay, so then let's go one step further. How are we dealing with path-dependent options, which are harder to price because the payoff depends on multiple points in the future? We use a similar idea to the basket option case, where we use different registers to represent the probability distribution at different points in time, and then we can create circuits that operate on these different instances in time to construct the payoff at the end. So an example here is a barrier option. This is defined on a single underlying still, but the idea is that the option is, and this is one particular version of it, only is valid if the underlying asset has crossed a particular bound, right? That barrier that we've decided upon. So the way we approach this is that we have these strike price comparators at different points in time, and then we calculate the another ancilla qubit on whether we've crossed that barrier at any point towards until the end of our simulation, let's say, and then we use that as a control qubit to see if to encode our payoff, which essentially means if it hasn't crossed, then don't really add anything to my payoff because the contract will be worthless. So we're able to code these up as well, and we're able to simulate it, and things are looking okay. We don't get any crazy dependency on any parameters that we add. And the last thing I want to mention is, okay, so we've played around and tried to come up with these circuits to encode the option prices into the amplitude of a qubit. But how does this approach compare to the possibility or the capabilities of devices today? Well, obviously, this is a long-term project in the sense that it relies on amplitude estimation, which is not a near-term algorithm, let's say. So we're not focusing on what we can use in the NISQ era, but more of what is the extent of, what is the reach of today's hardware, and what does it take for us to be able to use it at some point. But the full amplitude estimation circuits, they're too large to handle even in the simplest use cases at the moment. However, there are there's some approaches suggested that you can do amplitude estimation without phase estimation, which means that you don't have to take an additional m number of qubits and do the Fourier transform at the end, and you can focus on creating this A operator and then the essentially Grover steps or Grover circuits that will eventually be able to will be part of your circuit, and there's one particular approach which suggests using these measuring and running these Q operators and different powers of Q operators separately, and then combining the results using maximum likelihood estimation to get your final price. There was some work from Scott Aronson as well on this, which proves some tight bounds on this approach, which admittedly they're not really available for the approach that we're taking with maximum likelihood estimation. Now, for a simple European option case, we're able to construct a very simple circuit for the A operator, and even without doing any particular tricks with that, we can run it on today's hardware on the IBM Tokyo device, which has 3 fully connected qubits. And using readout error mitigation, we can get within 4% of the expected value of P1, which is the probability of measuring 1, which encodes our payoff. This circuit has 4 CNOTs and 8 Y rotations, and this will not give you any speed up if you run it. This is only one of the components that are needed to even theoretically give you a speed up, but it was something that we tried to see where we stand. Now the next extension is how does the QA operator, which is the first of these operators that we need to create and run to get the value of the option. So we've done some optimizations and some tricks where we can construct this Q operator, and we come up with 18 CNOTs and 33 single qubit gates, which we can still run. But the error on the measured angle is essentially of the order of 20%, and because of the scaling, the option price error is 60%, which is essentially nothing, right? Okay, so that's good. Let's see if we can do any better than that. Well, it turns out there is some work by our colleagues at IBM. They're doing this neat trick where if they want to mitigate the error of those 2 qubit CNOT gates, they can stretch the factor of each CNOT qubit gate and then extrapolate back to the zero noise limit, essentially, and get a more accurate result. At the time that we run this, we didn't have access to Open Pulse, or it wasn't available, so we did something even simpler. Well, okay, let's take every CNOT that we have in our circuit, and then let's replace it by 3 CNOTs, right? Of the same direction right next to each other. They'll have the same effect as one CNOT, because two CNOTs will cancel out next to each other. And if we put some barriers in between them and not let the Qiskit that we're using optimize this away, then we can get something like like we show on the graph on the right. So you have the dashed and dotted line is a simulated value of the option that we're looking at. We're varying the initial spot price of our distribution, and the green axis, this is the circuit unchanged, and then 3x and 5x correspond to the circuits that we run by replacing the CNOT by 3 CNOTs and 5 CNOTs. And then we can do this Richardson extrapolation and get back an error mitigated result from the CNOT errors. And as you can see, it's doing a much better job than we get just by running the simple circuit that we've designed without any error mitigation. And then we can combine this with the results that we get from running just the A operator and do a simple maximum likelihood a trick there, or a calculation. And then again, you can see here the blue line is the exact value that we expect. We have the results without any error mitigation and those with mitigation. And we can see we could brought down that 60% error to 20% error. Now that's a very significant error still, but our goal here was just to see where we stand and try to see what we need to do in the future if we're able to use this. So quickly, just some summary. Our goal here and our work has been to develop practically the circuits that are needed for doing option pricing in a quantum computing setting, and we started with something very simple and extended it with to add some more complexity. We tested the convergence compared with Monte Carlo in practice, and we evaluated the accuracy of a simple European option model on current quantum hardware, which I don't think it's been done before, or at least even in the attempt that we tried. And we learned about error mitigation methods to get the maximum performance of what we have today. And I will leave you with the fact that this has been an interesting work. There is definitely much promise, but there is a lot of work that we need to do to understand the individual circuit complexities and the optimal ways to construct them. So thank you. Yeah, that's all I had.
Thank you, Nick. Any questions? Yes. We have 2 microphones, so it's going to be less running this time, hopefully.
Thank you, Nick, for the nice talk. Question, do you normalize, I mean, you have algorithmic improvements, right, that you're making, but do you normalize them to, the computational speed differences, right? I mean, if you look at, quantum processors running in the megahertz per second versus, classical in the gigahertz, how do you account for that? Right?
We don't account for that. This is definitely only at the algorithmic complexity level. And there's a lot of questions there too, right? One of them is Monte Carlo we can usually parallelize as well, right? For amplitude estimation, the approach without phase estimation implies that you can actually do these operators in parallel as well. But again, there's no real proof of the real bound of that approach. But yeah, this in practice it remains to be seen what the result is. Yeah, we haven't done that analysis, and I think it will be hard to do as well.
Second question.
That's a great talk. Thank you. I just so one of the nice byproducts of the classical Monte Carlo is that you get error bars on your result. Do you get anything analogous to that? Is there any way to get something analogous to that, or have you looked at that for the quantum algorithm? Yeah.
So what you can do is that eventually you'll have the guarantee that you'll be with 80% probability or something within a certain bound, right? But I mean, in Monte Carlo, it's the same kind of idea, so I think they're comparable in that sense. But it's also true that in a lot of these settings, unless you have some qubit that you can say, you know what, this part of the computation is wrong and I should discard it. It's not very easy to make that judgment. But when you're computing these averages, I think that process of averaging, it gives you some confidence in the value that you get. I can't hear you very well, but
but there's other methods like using Sobel, right, where you don't use random inputs, but you have systematic inputs where you can get a considerable speed up in finding sort of the best answer, but you don't get that you don't know how close you are at the end.
Right. That's my understanding too. Yeah.